Hi, thank you for your interest in our project. I really hope you find this video useful, and I'll try to be as clear as possible. So, as the title says so, we are working on identifying how the toxicity of the fine particulate matter from residential wood burning varies with different combustion conditions. Let's continue to the background section to understand what are the reasons behind our questions here, right? It is not very commonly known, but residential wood combustion is actually one of the major sources of urban ambient fine particulate matter, also known as PM2.5. FYI, I will be referring to it as PM2.5 from now on, okay? Actually, residential wood burning can be accounted for up to 42% of the total PM2.5 emissions in North American urban areas, and some other groups have even found larger contributions in other European areas, up to 66%, so it's definitely a source worth looking into. Also, PM2.5 originated from wood combustion has been found to exert different toxic effects on both humans and animals. Oxidative stress via the generation of reactive oxygen species corresponds to one of the mechanisms that have been proposed behind the toxicity of wood combustion, PM2.5, and it is called oxidative potential, or OP. Finally, there is a myriad of studies reporting that the type of emission depends on how the wood is burned. So by burning in different ways, we will get different PM2.5 composition, which leads us to our hypothesis. We hypothesized that just as the type of compounds varies with the wood combustion conditions, the toxicity of the PM2.5 will also be affected by this. Some examples of combustion conditions that can be varied are, for example, the type of fuel, softwood versus hardwood, or between different species like spruce and oak. The ventilation can also be varied, or even the temperature at which the wood is burned. For example, low temperatures would correspond to smoldering burning, whereas high temperatures would correspond to flaming fires. So, how are we doing this? Well, as you can see in figure 1, specifically in the circle indicating number 1, we burn the wood in a temperature-controlled quartz tube furnace. We use either air or nitrogen as a carrier gas, and we collect the particulate emissions right outside furnace with help of a PM2.5 particle impactor and a quartz filter. The exhaust gases are then diluted and introduced to another chamber in order to measure CO and CO2 concentrations along the process. After all the PM is collected, we use the OCEC analyzer to determine the organic and elemental carbon fractions and ratios, and finally, we extract the PM from the filter and analyze its oxidative potential with the dithiothiol assay. I will be referring to the latter as OPDTT. Let's now move our attention to the results section, please. First of all, I would like to mention that the ventilation variation can affect the combustion in two different ways. First, the amount of oxygen available for the combustion depends on the ventilation air, of course, and secondly, this same flow can have a quote-unquote cooling effect on the overall combustion process. Thus, more air can both provide more oxygen, but can also decrease the overall combustion temperature. And just in case you are not very familiar with wood combustion processes, the higher the temperature is, the more complete the combustion will be. Okay? Okay. Now we can proceed to the results. We vary the ventilation in such ways that we could test the two effects we just mentioned. As for the cooling effect, we provided oxygen in great excess so that any variation in the flow rate would still provide enough oxygen for the burning. We can see this in figure 2a, and the results indicate that the OPDTT increases with higher ventilation. What this could mean is that the temperature of the combustion process is effectively decreased with higher ventilation, thus releasing more unburned and redox active species. As for the oxygen variation effect, we also tried burning with zero oxygen available to see how this would impact the final oxidative potential of the PM2.5. As you can see in figure 3, When less oxygen is available, the OPDTT is higher. Interestingly, we have some GC analysis preliminary results indicating that the oxygen content in the samples from pyrolysis, which is zero oxygen available, is higher than in combustion samples, which could be the lead cause behind the increasing oxidative potential between both ways, both tests. Supporting this, we saw that the OC fraction for each sample was following a very similar trend to the OPDTT. So you can see in figure 2b how we calculated the correlation between these two variables and found that there is indeed a moderate positive correlation. Finally, we varied the combustion temperature and found that the highest OPDTT was obtained during smoldering combustion temperatures, which in this case would correspond to 600 degrees and below. So, what are the keynotes here? Well, first of all, the positive correlation between OPDTT and the OC fraction could actually be helpful in connecting the extensive wood combustion database and the still a little bit narrow or emerging oxidative potential data for future health assessments. Secondly, we observed that the OPDTT increased when the wood was burned under oxygen-deficient atmospheres and also when the ventilation was too high and might have decreased the effective combustion temperature. Lastly, the highest OPDTT that we observed with varying temperatures corresponds to smoldering fires temperature, and the lowest one corresponds to flaming fire temperature. Some of our future steps are to include additional metrics for toxicity in order to have a more complete approach and understanding of other toxicity metrics. Two of these metrics that we have in queue are the electron paramagnetic resonance, which helps with the determination of the free radicals, and the benzoypyrene equivalent, which is fed with the measurements of the priority PAHs that we have been proved to be either carcinogens or mutagens. We would also like to test additional types of wood. Currently, we have tested one species of softwood, which is spruce, and one species of hardwood, which is oak. So what we're trying to do is to see if there are some other generalizations that can be made from the results that we are trying to get between these two types of woods, which are softwoods and hardwoods. I would also like to mention that this project is being supported by the Ontario Early Researcher Award and NSERC. And I would like to thank all my team from the Chan and Evans Labs for being so supportive and helpful. Below you will be able to find references I used in case you're interested. I would like to thank you for your interest in this project and for watching this video until the end. Please feel free to contact me if you have any question or comment regarding this project, or even if you would be interested in discussing any other ideas. Thank you very much and enjoy the rest of the conference. Bye bye.